हेलो एवरीवन। आज हम डिराक डेल्टा फंक्शन के बारे में सीखेंगे। सबसे पहले हम इसके ओरिजिनेशन की तरह कि ये प्रॉब्लम कहाँ से आई, सबसे पहले हम उसके बारे में जानेंगे। तो सबसे पहले उसके बारे में जानने से पहले लेट्स डू अ प्रॉब्लम वेयर वी हैव टू कैलकुलेट the divergence for a vector field which is defined as this vector field is v is equal to divided by r square along the direction r hat. Okay, so what does this mean? This vector field, if I plot this vector field, so how it will look like? The field lines will originate from here and they will decrease in magnitude as they go far away from the center. So this magnitude will reduce and the field lines will be radially outward. Similarly in the all other directions. Okay, so this will be all uniform. Okay, fine. So now let's try to find the divergence of this function. So what that will be? So that will be divergence of v is equal to, since we are using spherical coordinates, so that will be 1 divided by r square del by del r, then r square, the function, the radial part of that function. So we are, and then there will be theta and phi coordinates. But since there are no theta and phi coordinates here in this function, so we will just keep this form, and let's simplify this. So that will be del by del r and r square divided by r square. Okay, so this will cancels out and we have left with differentiation of 1, which will be equal to 0. So the divergence of this vector field is 0. But now, if I tell you an interesting fact, is that uh, if there is any function which has the maximum divergence, is this function only. There is no other function which have a higher divergence than this function. So, but we are getting the divergence as a 0 value. So why this is happening? So before getting the answer for this problem, let's try to calculate the surface integral for this problem. So consider a sphere. So let's say this is a sphere and of radius r, which has which is which is centered at the origin. So the surface integral will be for this vector function for the closed surface will be v dot dA. Integral this vector function which will have this r square constant over this surface of this sphere, and then r hat dot, and then this dA vector. So this dA vector for a constant radius surface will be r square sine theta d theta and d phi, and this will be along r hat direction. So this r hat will give you 1, and this r square will cancel out with this, and now you're left with only the integral over theta and phi. So theta will run from 0 to pi, and sorry, to 0 to pi, and phi will run from 0 to 2 pi. So that will be sine theta d theta d phi. So this d phi integral will give you 2 pi, and when you do the sine integral, so that will be cos theta, and then if you do this, then you will get a factor of 2 extra. So basically what you will get is 4 pi. So the surface integral for this vector field over the surface of a constant radius sphere is equal to 4 pi. Now use Gauss divergence theorem. So what it states is this closed integral over some surface of vector field V will be equivalent to the volume integral of the divergence of this vector field over this d tau volume element. So now if you notice, we have calculated this divergence of this vector field which came around to be 0, and we have also calculated the surface integral on the left hand side, so which is coming to be 4 pi, but we know that 4 pi is not equal to 0, so there is some discrepancy happening here. So why this is arising? So the actually the source of this problem is this center, this origin here at, since at r equal to 0, this vector function, this v at r equal to 0, it is blowing up to infinity, so that we can't do the this divergence, this integral. So that's why these two things are not coming to be equal. So this says that uh, so since the source of this problem is this origin, so this suggests that this divergence of this vector field will be 0 at every point outside this anywhere outside this origin, the center, but not at this exact. The vector field will be such a way that the surface integral of that vector field over any surface, this surface is arbitrary. So since this surface is arbitrary, arbitrary sphere, so of any radius r, so that uh, this integral should be, this total integral should be 4 pi, and this divergence of v should not be should be such that it should be 0 at every other point, but not at this exact position. So this suggests us that uh, this divergence of v must have this type of form, 4 pi and a Dirac delta function which is centered at origin. Now why this 4 pi factor is there, I will tell you. So what you can do is take the this volume integral of this side. So that will be v del v and d tau. So that will be nothing but 4 pi times this volume integral of a Dirac delta function which is centered at origin for this. So now we know that this since this whole integral is equal to 1, basically the normalization condition, so this volume integral will be equal to 4 pi, which is exactly matching with the Gauss divergence theorem or the surface integral value. So that was the solution for this problem.